Okay, this is Core Pure 2, Edexcel, June 2023, again last year's paper. And this is question 3 that some of you have been asking for me to have a look at. It's a matrices question with a little bit of transformations in there, a bit of invariant lines in there. Starts off quite nice. So you've got this matrix M, minus 2, 5, 6k, so just 2 by 2 matrix. You're told this identity works, or this equation, if you like, works, and we've got to determine the value of A and then show that k equals minus 9. So if we plug our m in here, we've got m squared, so we've got minus 2, 5, 6k times minus 2, 5, 6k. So that's our m squared to make the matrix times by itself. Then 11 lots of m, so 11 lots of, oops, that's not very good, thank you very much. 11 lots of m, which is minus 2, 5, 6k again, equals A times the identity matrix. So the identity matrix is obviously 1, 0, 0, 1. And if we times it by A, that's going to give us A, 0, 0, A on that particular diagonal. Right, now then, we could multiply the whole thing out and do a whole load of work, but actually we could just focus our multiplication out just on one particular entry, if you like. So if we're going to get this entry here, surely that's going to come from first row times first column, gives us our first entry. Then we're going to have to add 11 lots of minus 2 as our first entry, and that should give us A. So actually, minus 2, 5 times minus 2, 6. So that's going to be 4 plus 30. So minus 2 times minus 2, 5 times 6. Is that first entry in this result of that. We're then going to add on 11 times minus 22, so that's minus 22. And that should just give us A. So there's no need to multiply the whole thing out. We're just after what A is, so just concentrate on one particular term. So that first term, first row times first column, plus 11 lots of minus 2 will give us the A. And obviously we can work through that and find that A is 12. Okay, so that's not too bad to start with. Now then, we're now going to show that K equals minus 9 for part 2. So it's a bit of a show that. So again, let's concentrate on one particular term. Looking at this, let's concentrate on that second term, the 0 there, because that 0 is going to come from first row against second column, plus 11 lots of 5 should equal 0. And that, by doing that times that, we are going to get the k in there. So minus 2, 5 against 5k, so minus 2 times 5, minus 10. 5 times k, 5k. Plus 11 lots of 5 equals 0. So that leads to 5k, obviously 45 there, over the other side is minus 45, and lo and behold, there's k equal to minus 9. Nice little 3 marks to start with. Okay, so all done there. Now, remember k equals minus 9, so let's replace that k in there with minus 9 for the part B of this question. Now, the part B simply says, determine the equations of the invariant lines of the transformation represented by M. So invariant lines are different from invariant points in that they are a line of points that when you multiply it by that matrix, moves to another point on the line. Doesn't necessarily stay where it is, can do, but that would be an invariant point. So an invariant point doesn't move from where it is. An invariant line is just a line of points where one point will just move to another point on that line. Can stay where it is though still. So let's have a look at this. If we're looking for invariant lines, so obviously our lines, we can have an equation of y equals x plus c. So what we're looking at is taking this matrix minus 2, 5, 6, minus 9, timesing it by a coordinate from this line. Now you could just pick x and y and have like your y as mx plus c, but I'm going to just let x equal to a. Let's say we put a value of a into that invariant line. So our x coordinate is a, and if our x coordinate is a in here, our y coordinate will be ma plus c. So that is a point on x coordinate, y coordinate on y equals mx plus c, where x is worth a. Now that maps us to another point on this line. So let's call that x coordinate b, and that will map us to mb plus c. So a point on the line, a ma plus c, maps to another point on the line, b mb plus c. Now obviously a and b can be two different points, but the m and the c will be the same. It'll be the gradient and the y-intercept of this invariant line. So what we've really got to do is go, okay, matrix times a point on a line equals another point on the line. Right, let's multiply that out and see what we get. So minus 2, 5 against a, ma plus c. Minus 2 times a will give us minus 2a. 5 times that will give us 5 ma plus 5c. And apparently that's got to equal b. Then, for our second term, that row times that column should give us that. So 6 times a, 6a. Minus 9 times that is minus 9ma minus 9c. And that's going to equal mb plus c. Now, what we've got there is two equations, two things that we want to find, m and c, two things that we're not massively interested in, a and b, are just random points on these lines, random x values. However, because we've got b equals this, let's substitute b equals this into there, so we now just got something in terms of a's and m's and c's. So I'm just going to go down here a minute and put this in. So 6a minus 9ma minus 9c equals m times b, so it's m times this, so I'll do that in one go if that's okay. So minus 2ma plus 5m squared a plus 5mc, so that's m times b, m times that, plus a c on the end. So all I've done is I've substituted that b in there, and a bit of multiplying that out. Right, let's get everything onto one side, and let's group together the a's and then the constants. So I'll tell you what, let's take it all over the other side first. So we've got, let's take that 5ma squared and that 2ma over there. So we've got 5ma squared over there. Well, I'll tell you what, let's take that over there. Let's take them over that side, shall we? Give that 5m squared a plus 9ma onto this is going to give us plus 7ma. That seems reasonable, doesn't it? What else a's have we got? Oh yeah, and then minus 6a over that side. Okay. So that's all our a terms over that side. Now let's look at what constants we got on this side. So plus 5mc plus, now then, that 9c going over there is going to give us 10c equals 0. Okay? Right, let's do a bit of factorising out here. Let's factorise out this a. A 5m squared plus 7m minus 6 plus, let's take the c out here, c 5m plus 10. Now the m and c are things that we're trying to find. The a is just some random point, you know, x equals 2, x equals 7, whatever. If it's got to equal 0 though, 0 that means, we've got the number of a's on this side is equal to 0 a's on this side. And the constant on this side is equal to, which is 0, is equal to 5c times 5m plus 10. So we kind of almost like equating coefficients, if you like. So we can do that 5m squared plus 7m minus 6 will have to equal 0. Because whatever A is here, we've got that many A's on this side, but no A's on that side. So we've got to have the same number of A's on either side. So that must equal 0. Okay? So now we can solve that. Either put it in your polynomial solver, or if you like, try and actually factorise it yourself. I'm going to now look really stupid by not being able to factorise it. 2 and 3. Oh, I can. There you go. Plus 3 there, and minus 2 there. Is that right? No, it's not. That's plus 2 and that's minus 3. There you go. I've looked stupid. So, m here would be 3/5, or m here would be minus 2. Okay, happy with that. Right, now then, I'm just going to rub this off up here if I give myself a bit more space. So we've actually got to the potential gradient of our two lines. We know it's going to be y equals 3/5 x and y equals minus 2x plus c's, obviously. And the two lines, therefore, we found that are invariant. Now let's come to the c part. Now, for the c part, let's look at if m was equal to 3/5. We know this is going to be equal to 0. Okay? So, if we make that equal to 0, c times 5m plus 10 equals 0. If m is equal to 3/5, if we put that in there, c, 5 times 3/5, well, that is 3. Yeah? So, we've got 13c equals 0. Well, that can't happen unless c is 0 itself. So for m to be 3/5, we have to have c equal to 0. So straight away, that's one of our equations. We know y equals m, 3/5, plus c, but we worked out that c would have to be 0 in this particular situation. Okay, now let's look at the other gradient, m equals minus 2. So, here we go. If m equals minus 2, go back up to this, so c times, putting 5 times minus 2 in there, we get minus 10. Oh, look at that. We get 0 there. So actually, c can be anything we like. It doesn't matter. So our second set of invariant lines will be y equals m minus 2. Our c, anything. It can be absolutely anything. So it says, determine the equations, the invariant lines of the transformation represented by m. We've actually got an infinity number of lines that fit that. Y equals 3/5 x, that's a very specific one. And then y equals minus 2x plus anything we like. Okay? And so it would probably be worth letting the examiner know that I know c can be anything there. Right. That's quite an interesting result with that c being anything. So I wouldn't just like pick another one or something like that and say, oh, y equals minus 2x plus 3, although that would be correct. But you do need to make it clear that, oh, actually, there are an infinite number of solutions for that. C could be anything. So have a little sentence in there saying C could be anything. Right. Now then, what's the part C? State which, if any of the lines identified in B consist of fixed points, given a reason for your answer. Now, if they are fixed points, so it's just a daft way of saying they're invariant points. Their points don't move. So what we need to see is a particular point being mapped exactly to itself. So let's have our minus 2, 5, 6. I've forgotten what k was. What was k? Let me just remind myself. We got k equals, k's minus 9, wasn't it? Sorry, minus 9. So, If we times that by a particular point on this line, a random point on that line might be A and then 3/5 A. Because if X is A, Y will be 3/5 A. And it's got to go, oops, sorry, that should be an equals there. It's got to go onto itself, so A, 3/5 A. Now what we're now going to do is check, does that work? So let's do -2/5 times A 3/5 A, so -2 times A, 5 times 3/5 A. And that does indeed equal, it's got to equal A, so -2A, 5/5, so that is 3A, and oh, that equals A. So that works for that particular point. Now let's check it works for the y-coordinate as well. So 6 minus 9 against A 3/5 A. So 6A minus 9 times 3/5 A. Let's see what that gives us. So 6A, 9 times 3/5 is minus 27/5. Oh, and that's 30/5 A. So, oh, that's 3/5 A. Yes, it works. So, y equals 3/5 X, it works. Each point gets mapped onto itself, so it's a mixed point. So, let me just, excuse me, just get my thing back up. There we go. So it says, state which any of the lines identified in B consist of fixed points. So y equals 3/5 X consists of fixed points. Now let's check the other one out. Now it's going to be a bit more difficult because it's y equals -2x plus c, where c is something. So but let's just multiply it through, -2. I know this is just a one marker, so I'm probably going about this way too much work. But this is how I would do it. So let's take a random point, A, and -2a plus c. And we've got to get A and -2a plus c again. Well, let's just see if that works. Let's take this first one, -2/5 against AC, so -2a. 5 times that gives us -10a plus 5c. And that equals -12a plus 5c. Oh, we do not get the same as A, so it doesn't work. So y equals -2x plus c is not consists of fixed points. It's just y equals 3/5 X consists of fixed points. Done. Okay, hope that makes that sense. That's quite an unusual question really, but this idea of getting invariant points and just going, right, y equals mx plus c, that bit that we did before, and going, right, let's have a and ma plus c go into a and b and mb plus c, and working through like that. It's quite an interesting kind of technique to use. Okay, thank you.